Alright. So we said that the final is going to be on everything, including this section, condensation and boiling. I know it's the last thing that we are going to cover, but this is also could be included in the final exam. Right? And so, but for boiling, we said that all we have to worry about is this equation. This is Q nucleate boiling, and we had a homework on that, and the equation for the Q maximum or Q max critical heat flux, and this is the equation for it. Right? And we finished by that last time. So the rest of the boiling section you don't have to worry about, but still I would like to show it to you. I would like you to understand that once you go through this peak, the Q actually dropped because of the film boiling, and this point, Q minimum boiling, minimum film boiling, that's the relation for it. And again, those constants are pure experiments, but those guys are coming from having a theory for explaining why this is the case. Right? And this is Q for film boiling. Right? Again, we are not going to solve a problem over this. Right? So don't worry about actually solving problem over it. But just know that once the film boiling start, and it's really that's the lowest point in the heat transfer. As the TS increase, this Q start to increase. So I can ask you multiple choice in the exam. I will not give you the equation, but I could ask you basically something that will show that you understand that Q with film boiling could be actually as large as Q nucleate boiling. Alright? So the fact that you are doing film boiling doesn't mean that the Q is not as large. It's very large, but on the expense of very, very high TS. Right? It's very, very high TS. And the reason why it increased, despite the fact that the whole surface is surrounded by film or vapor, it's because, well, the TS is really large. So just pure conduction even will do very well even in something like this, just because the TS is very, very large. And on top of that, there is also radiation. And look at this. This is the radiation per unit area. So it's as if the base over here is surrounded by this water. All the radiation leaving the base go to the water through the vapor. Right? So TS to power 4 minus T saturation to power 4. Right? And he said that the Q total will be Q film by plus 3/4 of that Q radiation. And this is what Jesse almost invented last time. Remember when he talked about let's have holes in the base to improve the places where the bubbles get created. Right? So this improved the nucleate boiling. It actually can increase nucleate boiling by 10 times. So that's pretty here, 10 times Q. If you actually have the wall artificially drilled or roughened to make the place perfect for creating those bubbles. Right? And so this is where he said this is just like roughness. When surface is rough, eventually this roughness effect decay with time. Why? Like when you start with a rough surface, you see very, very strong heat transfer by boiling, nucleate boiling. But by time, as this machine gets older and older, or this boiler gets older, that effect will deteriorate. Why would you think this is the case?
Over time, the
erosion smooths it out. It get oxidized, and then, or even this roughness element is not really that strong attached to the paste, so they can get broken. So to permanently keep it that way, they drill it such that it's not just elements peeking up, but it's really very well constructed holes. Right? This was called nucleate boiling. Right? Nucleate boiling it's a pool boiling. It's basically you have this pot or you have this big container where the water is boiling at the surface. The other mechanism for boiling, or the another scenario, is flow boiling. So the flow is moving in a pipe. While he's moving in a pipe, the pipe is being heated by the flame around it in the big boiler, or it's basically the flow is actually moving between nuclear rods. So those nuclear rods, the water would be moving through them, right? So the water would be as if it's moving inside a pipe between those very hot walls, because there is nuclear reaction happening inside them. All right? So this is called flow boiling. You are boiling while you are moving. So chances are this would actually be stronger or weaker compared to pool boiling when it comes to the flux, the Q that it can remove. Stronger or weaker if we let the water move while it's also boiling? Stronger, right? Why did you think this, Jose?
Because it's already boiling.
No, but why moving the water will improve the heat transfer by boiling?
It distributes the heat.
I think it's because it moves the bubbles also quicker. The bubble don't have to wait enough time until they build up and get out. The point the bubble get created,
So it replaces the bubble with more liquid to become.
I think the mechanism of removing the bubble get much stronger. But also the fact that you can create turbulence, that's for sure, because water is at the new water is how much new water? Remember the Reynolds number is Vd over nu. So what will determine really laminar or turbulent? Not just V and D, it's nu. So nu for water is, anyone? 10 to minus 6 meters squared per second. So you can cancel this and multiply by 10 to power 6. So Vd multiplied by 10 to power 6, that's the Reynolds number. So anytime the water is moving in a decent pipe, not 0.1 inch pipe, but a decent pipe, 0.1 meter, 10 centimeter diameter, 0.1 meter multiplied by 10 to power 6, already 10 to power 5. And so the V can be anything. And the Reynolds number is already turbulent. So that turbulent make huge mixing, and of course it improve the temperature distribution along the walls, right? And wouldn't really let any hot spot happen near the walls. So as a result, that's what you see. This is the nuclear boiling without any flow, and once you increase the flow velocity, it go like this and go like this. So those are the convections. Of course, the convection gets stronger and stronger. Again, we're looking at the Q against the delta T. So of course, the convection, pure convection, natural force of convection is much higher. Remember, this was a log scale. That chart was log scale. So it's not like twice as much. That's like 10 times as much. This is 100 times as much. And nuclear boiling also increase. All right? Because what they do to basically improving how the bubbles get rid of and the distribution. Right? So flow boiling improve, especially when it's external flow boiling. If the flow is moving on a hot surface and the bubble want to just sit there until it's big enough and get bigger, it immediately gets squished out of its way. It's basically it's removed very quickly. And when it's internal flow boiling like this, also you see improved heat transferring. And so, but one thing about flow boiling is that the bubbles actually, when they start leaving the wall, they eventually get closer to each other, and there are so many of them to the extent that they join together and they make huge bubbles inside the pipe. All right? And so it's called slug flow. The flow would be surrounded by, so originally you have bubbly flow, a bunch of bubbles are moving with the flow, and then it becomes slug flow. That's when you have huge amount of bubbles joining together, making these giant bubbles leaving, and then you end up having something like this. It's called annular flow. So a vapor core in the middle surrounded by liquid film. And then eventually you end up with vapor with just a bunch of droplets maybe inside in the middle. So the flow flip, rather than water with bunch of bubbles, it's vapor with bunch of droplets. And this is called mist flow. Just bunch of droplets moving around. And eventually even those, this also evaporates. right? And you just have pure vapor, not air, vapor, pure vapor, right? Gaseous flow. And so you can explain, this is, he's plotting for us the temperature. You can also, this would be the temperature, but also the, in this case actually it's the H. And you can see why suddenly the H will drop from you. It dropped from you because you end up losing the boiling mechanism. When you, now the air, the pipe is surrounded by vapor. It's not surrounded by liquid anymore. And that's why what make the H rate drop like this. Right? And so there are models to basic and correlation to describe each part of this process. What's the H over here, what's the H over there, what's the H over there. And they study those things in detail. And if you have a program that will say try to simulate what happened in your boiler or inside the nuclear reactor, he will have to include all those correlation that for each one of them. Right? Boiling while the flow is slug flow, boiling while it is annular flow. Right? Right, so now the final part in our course, condensation heat transfer. So that's almost the opposite of boiling. So that's the other part, you know. So in any HVAC machine you have boiler and you have a condenser. The boiler is your evaporator that's inside your house where the freon bubbles and take the heat from your house and make bubbles. And the other side, that's the condenser outside where the vapor, the hot vapor condense and become liquid freon. Alright? So we will solve those problems just like we solve any natural or forced heat transfer by convection. The main equation is QHA delta T. Right? It's just the H, how we are going to come up with the H. And just like for the boiling, there was H for boiling. Remember that big equation? There's also here an equation for that H. Right? So don't worry about so many formulas in this chapter. All you care about is for this film boiling. And for this is called dropwise condensation. So that the vapor is condensing as basically a bunch of droplets. That's your shower wall in the morning. And start making, but you know what happened after that, right? First you have those bunch of bubble, or sorry, bunch of droplets, and then what happened after that? If you take shower, if your shower is long enough and keep watching, those bubbles, those droplets will start doing what? Falling down. They join and they end up eventually bringing themselves to a film boiling. So just become a film falling. Alright? So of course, which one of those, if your job is to actually to improve the heat transfer by condensation, you would like to send as much heat as possible from the wall to the film, right? That's how we can, the point is to take Q from the wall. We are cooling the wall by condensing, right? So if your job is to get as much Q as possible, which mechanism you would like to use? Film condensation or droplet-wise condensation? Which one will make the Q higher? For the same what? Same delta T. Ts and T saturation. So the liquid is condensing, or the vapor is condensing at T saturation, right? So he's probably, if it's water, at atmospheric pressure, it will condense at 100. While the water, the wall need to be cooler. The wall is at 80, so that it can actually manage to make it condense. Huh? Sorry, I did this wrong. So we actually, right, we give the Q here. I'm sorry, I flipped the Q. So again, 180. So which one will improve the heat transfer by condensation? Which one will make the Q even bigger?
Film.
Huh? The drop or the film? The film? Why?
Because it's more touching the vape or liquid. There's more contact between the liquid and water.
Think again. It's the dropwise. Why? The dropwise will actually make the Q higher.
Because it's in place more often.
That's my question. Why the H is higher? For dropwise condensation, why does it, the H actually is higher, and why they would love to keep it always at dropwise condensation? Say that again. No, those droplets don't stay at the same place. Those droplets form and then fall down.
Because the droplets are being replaced by new droplets, which is causing, it keeps it.
Isn't it because there's surface area on the sides of the droplets that can contact air and the film is the side that touches water?
No. So where is the heat transfer is happening exactly? The heat transfer is not happening through the droplets. The droplets is the end result. The heat transfer is happening between the vapor that's at 100 and the surface is at 80. And this is a problem because
Because it's a resistance.
it's a resistance. You are separating that film, that form, that's a resistance. Now, that 100-degree vapor find itself next to not 80-degree water anymore. He find itself next to,
85, 90 degrees.
right, he find itself next to a hot film of liquid, hotter than the colder wall, right? So, but if we expose the vapor always to the surface, that make delta T bigger, that make the Q really, really big, right? But so they do everything in their hand to maintain the droplets in their shape like this. How they coat the surface with very thin film of material that increase the surface tension. It actually increases how the surface is hydrophobic to the water. They make the surface hit the water.
Like a wax.
Like a wax, exactly. And so the moment the droplet sit there, it doesn't wet the surface. It remains as a droplet. You know, if you put water on a surface that like the water will split. But if you have like raincoat and you put a water droplet in it, the water droplet is supposed to just slide on the coat, not really set. Why? Because the surface does not like the water, and therefore the droplet will sit like this rather than sit like this. Alright? So eventually, of course, this treatment doesn't last because that wax layer or whatever they are using will deteriorate after a while. And the surface go back to its original nature, and then they lose this droplet-wide condensation and become film condensation again. Alright? But think of this film as nothing really helping you. It's something that's annoying the heat transfer. Alright? So what kind of problem I could ask you about in the final? I will ask you, well, how much m dot per unit kilogram per second that's condensing? Well, how you are going to get that? Q equal
That's CP, that's
m dot HFG. Q dot, the heat transfer, is equal to m dot, the kilogram per second, multiplied by HFG. There is HFG that we are using it in reverse this time. We are not boiling it. No, we are condensing it. So we don't need the wall to give us the HFG. We are actually going to give the wall the HFG. But still, the equation is Q dot is m dot HFG. All right, and so to get the m dot, I need, so m dot is what's actually unknown. I need the Q. How am I going to get my Q? How you get the Q for something like this? Anyone? MCB delta T? No, this MCB delta T that you guys keep throwing it at me, that's only for a fluid that's being heated or cooled across a single phase, meaning that he come water and he leave water. Then Q dot is m dot CB delta T. Or he come as air and he leave as air. Sorry, vapor and leave as vapor, gas and gas. Then it's the Q is m dot CB delta T. Right? Anytime you have a phase change, he does not change its temperature. So the vapor here was at 100 degree, and he condensed to be 100 degree. All right, except that that film will see there's a temperature distribution inside it too, because the wall is at 80. So that part of the film must be at 80, but the part near the vapor probably at 100. And then you have a linear distribution or some distribution between the 80 at the wall and the 100 at the film. So back again, I need the Q so that I can get the m dot. How am I going to get the Q? Huh? HA delta T. HA delta T. And it's the job of that chapter to tell us how to get this H. All right? So now, fortunately, this particular problem, they can actually drive the whole thing analytically. They don't have to depend on experiments. For a laminar flow, for a laminar flow, that's very easy to come up with that solution. And don't worry about how did they come up with that solution. But I would like you to see it. But I will not ask you to drive it. You will just care about, let me jump to the equation. So the equation would be this. This is the equation that we will use, right? But I still would like you to see how did they come up with that equation. So it reminds you of the H for the boiling, right? Because it has G and it has rho and rho vapor and it has mu L and all the good stuff in it. But let's see how did they come up with this. And so the film. So this is for condensation on a vertical surface. We will see equation later on for the condensation on a horizontal cylinder, bunch of cylinder one after the other. So, but for a vertical plate, condensing on a vertical plate, that will happen. That the droplets will start showing up over here, and they will join, and you will have this continuous film. And the film gets thicker and thicker as we go down, because why it's getting bigger and bigger? Why it's not just constant film? Huh? That's not a good reason. The fact that it's falling down doesn't mean that you need to increase in size. Why the thickness is getting bigger? So that thickness is called delta.
Between the liquid and the wall.
Say it again, Jesse.
Between the wall and liquid.
The pressure? No, everything is atmospheric over here, by the way.
Friction. The water droplets slow down as they get to the bottom.
So there is a velocity profile, and that velocity profile is like this, and that velocity profile is because this wall is not moving, and the fluid next to it need to be the same velocity as the wall. But that's not the reason why it's getting bigger. So yes, Jesse is right, there is a velocity profile. That doesn't explain why the thickness is getting bigger.
Is it just because there's more surface area before condensation can happen?
Exactly. And so Cameron is saying it's because over here there is a bunch of droplets that end up condensing. Over here there's a bunch of droplets that is being condensed. So at the end, this is basically that flow rate, that m dot that's moving here is the m dot coming from all those surfaces. Every place the droplets are condensing. It's not just condensing only at the tip. The droplets are condensing everywhere. And so at every station, you are basically accumulating everything that happened before you. So of course, at the end, that is the largest flow rate, because it has basically accumulating everything. All right? All right, so now, what do you think if you are trying to find out a plan to calculate this H, the H that we are going to say that the Q dot is HA delta T. How you are going to calculate this H? Any idea? So when we say that the Nusselt number is HL over K, that's basically relabeling the problem. It's basically, when I'm telling you, how much did you get in this exam? You will tell me, well, it's a letter grade. All right, so what is a letter grade? Did you get A, B, or C? So when I ask how did you calculate the H, you say, well, let's calculate the Nusselt. Well, it's just putting it next to a K and D, but still we didn't recalculate the H. How do you calculate the H? What do you think? So I'm not asking you to come up with an experimental formula. I'm actually asking you to calculate the H. If there is any equation that have the H in it, or yeah, any equation that has the H that can calculate this H. What equation does it have the H in it so that we can calculate the H from it? Huh?
I'm just saying, there's Q dot, there's neutral.
There is Q dot, the Q dot which is HA delta T. I bet we have to calculate this Q from somewhere else so that we can calculate the H from this one. No, we can't. That's just too much. We can calculate also Q conduction, because eventually that Q, that's, and Brandon is right that this Q is m dot HFG, right? That's true, but that Q that's actually given here, it's also eventually have to go to the wall. So they actually thought that, well, to calculate this Q, if only we have what? We can calculate the Q to the wall. Huh? The gradient. How you are going to do with it? What are you going to do with the gradient of the temperature? Q conduction is? Anyone remember chapter 2? Q conduction is? Huh? Obviously, right? And that's why we will calculate the H from it. So beside this, just Q conduction and the gradient. What's the relation between Q conduction and the gradient? Chapter 2, guys, what did you do in your first exam? Or Q is minus K multiplied by dt dx. That's how we eventually turn it into Q is delta T over R. But originally, the Fourier law was Q was minus K partial T partial X. So knowing the gradient of the temperature, you multiply this by K, you get the Q. Right? Correct? So they are after solving the temperature profile inside this film. Of course, solving the temperature profile inside this film means that you actually know the height of that film. So you know the geometry that you are dealing with. Will the height of that film depend on m dot HFG? Right? And m dot HFG will also depend on the Q. So it's actually a bunch of equations that they have to solve them together. So I will let you read the solution yourself, but as an undergrad, I really enjoyed reading it. And how did they couple those equations together to come up with this? Right? But I'm not going to ask you to actually drive it yourself. Right? But it's really pretty because you have to calculate Q conduction at the wall, but also you have to know the thickness of the film, and thickness of the film depend on the Q. Alright? So to come up with the thickness of the film, you need to know what's the m dot over here. And so they solved Navier-Stokes equation. So this is basically Navier-Stokes equation in this part. And you see they can calculate the velocity profile if only they know the delta. Delta is the film's height. Okay? So the solution is not really there yet because they don't really know the film height. And then m dot, how much mass is flowing, it's function of delta. The mass flow rate that's moving, yes, it's integrating the velocity profile. It's m dot is always rho VA, but they don't really know the area until they know the delta. And so you can see m dot is function of delta. And then they say, well, that m dot or the Q is basically related to m dot by Q is m dot HFG. And that's the part when, so they basically say any m dot that we add that means that Q is moving through. Alright? And over here, so here is the Q dot equal M dot HFG for that small element, and here is, what is that? Does anyone see this? This is Q dot is this is Q conduction. K partial T partial X multiplied by the area. Right? That's Q conduction. So delta Q is equal to, or Q dot is Q dot conduction at the wall, and it's also equal to M dot HFG. And so from all this equation, they can manage to get delta X as function of X, or basically they can manage to get the H. And so here is the H. And so the H, and so that's what we really care about. The H is function of X, meaning the H at the beginning of the plate is not the same as the H at the end of the plate. Why? Condensation is really different from the beginning till the end. The Q that the wall is sucking from the top is different from the Q that the wall is sucking at the end. Why is that? Different? Excellent. Excellent. Jose is saying because here you have different resistance than this one. That Q conduction that you wrote over here will be different. And that will make the Q different. Yes, you have the same temperature difference across. Wall is sitting one side, T saturation on the other side. But the film is bigger and bigger and bigger. The Q is getting weaker and weaker and weaker. So if you are designing this thing, do you want to make it really long or do you want to make it short and wide? Short and wide, right? Because the longer it gets in the flow direction, the less effective it is. Right? So those are the kind of questions that I could ask for multiple choice that really show that you really understand the physics of the problem. Right? So it requires you just to inspect the formula and think about it. So because H is not the same everywhere, at the end of the day, I would like to calculate my Q. When I say H A delta T, I don't want bunch of A's, or bunch of H, I just want one H, probably H average. How can I get H average? Integrate over the whole thing, right? And so they integrate over the whole thing, and from that, it turned out that the result of the integration, because of the power of the X that you are integrating, see this X, you are integrating with respect to X, so this 3 will set the power. It turned out that H average is 4 over 3 H at the end of the plate. So you find out the H of the end of the plate, that is the lowest H, right? And you multiply by 4 over 3. So the average is 4 over 3 the H at the end of the plate. Alright? Or in short, you get this. This is the H. Alright? So 0.943, of course, so once they set up all the theory, still they need some tweaking from experiments. So 0.943 G rho liquid at T saturation, rho liquid, rho vapor, mu L, T saturation, Ts. L, that's the height of the plate or the length of the plate in the flow direction, not in the width direction, right? The width doesn't matter. It's the length. And KL, that's the conductivity of the liquid. And this HFG star. Why it's not just HFG? Anyone? Look at this. HFG is HFG star, that the one that you are going to use the formula, is HFG plus 0.68 CBL T saturation minus TS. Why? Say that again. Evaporation, that's HFG what it's for. But why they're adding more? So they are saying that to make that condensation happening, it's not just HFG that we need to pull from you. We pull even more. Why? because the film here is not a T saturation, it's a TS. So not only you have to take HFG from them, the film that leave is subcooled liquid. So he's basically subcooled. He doesn't go all of it as TS, right? Not all the film get cooled down to TS. So 0.68. And here is your CB delta T that you have been always worried about. Because now we are cooling the liquid from T saturation somehow close to TS. Not totally to TS, otherwise we would have used CB T saturation minus TS, but you get 0.68 of it because of that temperature profile. Alright? And so that's it. So this is again for laminar flow. Once you become turbulent or wavy, there are different correlations that I don't want you to worry about. I just want you to worry about laminar film. Alright? So for laminar film, here is the H. We multiply this H by A, we multiply by delta T, and that's our Q. Alright? And that Q is M dot. That Q dot that we'll calculate is going to be M dot multiplied by what? Think again. Multiply by no, HFG star. So the price now for that is a little bit more expensive. It's not just HFG. It's HFG plus 0.68 CBL T saturation minus TS. Or sorry, TS minus TS. Right, T saturation minus TS. Why? Because again the film not just condensed to be saturated liquid, but he end up getting a little bit subcooled. Right? Again because of the temperature profile. Here is TS, sorry, T saturation, but then he go down all the way to TS. Who's doing this cooling? It's the wall. Turn it to liquid and it cool you down a little bit more. Alright? So again, don't worry about the when it become a little bit wavy and when it become a little bit turbulent, there are different formula for it. Let's not worry about those guys. Alright. Now for inclined plate, what if the problem has an inclined plate and not vertical plate? Imagine if you have horizontal plate, will this mechanism work? Those formula will work? Probably not, right? The gravity is not pulling. When they come up with that solution, that was depending on that the gravity was pulling all the film down. So if you have inclined plate, you calculate it as if it's vertical, but you know that you will not take all of it. There is a fraction of it. How much is the fraction? Cosine theta to power 1/4. So if you have a tilted plate, you calculate H vertical and he give you the formula over here. It's the same formula that we had. But then you would say, let me have cosine theta to power 1/4. Where theta is how much you have to. So of course if theta is 0, cosine 0 would be 1 and you will get the whole thing. Right? Cosine 90 is 0 and therefore this equation is not valid for horizontal surface. This equation is just for a little vertical or a little bit off vertical. Alright? Horizontal cube and surface and spheres, that's the H for them. So this is just like natural convection when you have a bunch of formulas for H, each one of them for different configuration. Alright? So it would be hard, right? Because it will just be as if it's
Unless they have so much for the
yeah. And here is horizontal tube bank. So this was a horizontal tube, just one, right? And he's telling you that for a sphere we replace 0.7 by 0.815. Now for bunch of tubes, one expect the H to get bigger or smaller. What do you think? If you have a bunch of cylinders that are condensing one on top of the other, it will get, I'm asking about the H, not the Q. Of course, the total Q will get bigger because more and more what? Area. Right, more and more area. But the H would increase or decrease? Why? Well, that's so Jacob is saying, well, look at the equation. I mean, h for a bunch of tube is actually h for one tube divided by n to the power 1/4. But physically, why do you think this cylinder sucks? It's not really doing a good job at all. Why? Compared to this one. Yeah, you had all this film that's actually dropping on it. Right? It has been heated up by all the hot film falling on it. Right? So that it doesn't have a chance to make its own film. You know, starting from scratch and building it and right? All right. And finally, in this part, they are saying that if our condenser have beside the vapor, so the turbine where we finished all this, the steam was really hot and we end up expanding in the turbine, and then the turbine end up driving our generator, and now the turbine exhaust is going to the condenser so that we condense it, become liquid, and then pump it into the boiler and start the whole thing again. If this managed to get some air inside, not just vapor, but even bunch of air, and where would the air come from? Well, don't forget this turbine from Thermo too, if you remember Thermo. What would be the typical pressure inside the turbine? For a power plant, a steam power plant, this pressure would be low. How low? 0.07 bar? For some, compared to 1 bar? 0.07 compared to 1 bar. So this thing is under vacuum at the end. So any leaks anywhere would actually bring air in. So having air inside the condenser is bad for the condensation. Because here he say because all those air particles prevent the vapor from going to the wall. But there is another effect too that's really bad, and that is the vapor sitting in that condenser now. Let's assume that we are supposed to have 0.07 bar. That's the whole pressure inside the condenser. The vapor will have a pressure of 0.07 bar or higher or lower. Lower because lower because that's the partial pressure. When you have mixture of gases, each one of them has its own mixture partial pressure. So the 0.07 divide on them. So now, so the air is occupying some, depending on how much air, and the vapor now is not at 0.07 bar. Let's call it 0.06 bar. So at 0.07 bar, he was supposed to condense at a certain temperature. I don't know, I don't remember what's the condensation temperature. Let's call it 40 degrees C. Let's call it 50 degrees C. At 0.07 bar, T saturation is 50 degrees C. Okay? I'm assuming it's 50. Let's check the steam table later on and figure out how much. Now at 0.06 bar, what do you expect T saturation? 40. And the wall didn't change its temperature. The wall is what controls the temperature of the wall? The water coming from the river, Arkansas River, for example, into the condenser to cool it, right? That's the cooling water that's cooling the steam. So the water didn't change its temperature. And what happened now? Now the vapor is sitting not at 50, is sitting at 40. Will he ever condense? Not really, or at least his rate of condensation will drop. Why? Because he's sitting at temperature, his T saturation is lower now. Right? And that would require us to either cool the water more. How we can do this? It's already hot outside, so there is no chance we can cool. But maybe drive the water even faster so that it wouldn't even, because remember the water actually, as it goes through the condenser, its temperature would improve or increase because it's taking Q. So it come at 40, it leave at 45 or 50, right? Anyway, so for whatever, this is why it's bad to have air leaking into the cycle, and you don't want to send it also to the very hot boiler with very expensive pipes. You don't want to have oxygen at that temperature next to those pipes. So in the cycle, before they send that vapor into the into the boiler, they have a place where they call the aerator. You vent all this extra air. Alright? So the aerator would be a place where the pressure is above atmosphere, higher. So they pump the condensation a little bit, and in a place where it's above atmosphere, they try to separate the water vapor from the air, and they vent, and then the air would go from the top. Alright? Right, so that's the drop-wise condensation. And again, we would love it, but it's just very hard to maintain, right? And see, as a droplet start falling, it clean everything, leaving an empty place behind it, kind of. If it's really very pure drop-wise condensation. And here's your etch. All right? So you can see that the etch is probably very high. And I'll finish the course by this. So in the International Space Station, when natural convection fails you, right? Natural convection will fail you because hot air around our transistor or computer will not go up. They will just sit around our computer, right? And the computer will get soaked in its basic. Imagine if CO2 that we freeze back, we exhale, does not go away from us. They actually go because our nose is designed that, this is our nose. This is your mouth. This is your eye. So when you exhale really far away. But when you inhale from very close by. You will hear about this in fluid mechanics, in experimental fluid. But the point is, we have a mechanism to send the CO2 away from us and bring fresh air, or O2 to us. So this doesn't happen then in natural convection in space. You cannot send the heat away from you. So how do they get it out? How do they can make the heat go away? They use this. So this heat pipe, it can take the heat away from you very effectively. You could say they could depend on alternatively conduction. Why don't just have pure conduction? Right? Like let's have a copper tube in near the processor, and this copper tube will go away. So the copper tube, if it's have very good conduction, it will be all hot. And so everywhere along this copper tube, you know, like this copper tube, and the copper tube will be surrounded by fins, and therefore that heat sink will basically have its heat conducted and disperse it far away from it, right? But that heat pipe is even much stronger than conduction. How we can improve the heat transfer between this place to the other place? Boiling and condensation. So this thing have a boiler and evaporator inside, and a pump that convert the two things away, or send the flow from one side to the other. So where is the pump? The pump is this material. Look at this. So the surface is basically some kind of napkin-like material. Wicking. You know wicking? When you go home, try this, spill water on your table, put a napkin on the water, what will happen? The water will climb up, right? It doesn't care about gravity. It will climb up. So in space, this will also climb up. The water will climb up from the place where the water is a lot to the place where the water is little. Where is the place where the water is a lot? That's the place where it condenses. So the vapor go to the cold place, condense, become water. And the place where it's really hot, that's near the processor, that when it boil. And so you have to have the right pressure here. This thing should be at the pressure where a little bit will boil it, a little bit heat, a little bit lower temperature will condense it. And so you have high concentration of water, low concentration of water, and this pump is continuously bringing the water from here to here. So bring the water so that it boil, and the vapor, because it has large volume, he doesn't have to depend on the wall to move. He will just, by its pressure, the moment he forms, he will just fill the space, all right, and go to the other place where he will end up condensing, all right? So it would be something like this. So the heat will get sucked, and then over here you will basically have a lot of surface where the Q can leave. And this actually doesn't have to happen in outer space. We can actually use it in application where you just don't like natural convection. It's not working for you. So you basically depend on boiling condensation and conduction and wicking to do this trick, right? And so here's a different material or different fluid that you would use, and this is the temperature where they would boil at. So that would basically tell you the boiling and the melting point where you can, and so that would be the useful range that you would use something like this in a heat pipe, right? You want them to boil in one place and condense on the other, right? And we are done, and it was great. Thank you so much. And the evaluation for this course will be online. They either send you the link or they will send you the link. You will get an email and you just fill the evaluation online. Did you get the link already? Not yet? It will be sent to you by email, and then you can do it. The exam is on Wednesday at 6 in the same place. Open textbook, 2 pages of notes, your calculator, and 2 hours. 6 to 8. Questions? All right, good luck. Study hard. The exam is comprehensive, correct. But chances are, I'm focusing on the part that I didn't ask you in the first 2 parts. But it is comprehensive.
Is there any way